Hi, my name's Tracy and welcome to the channel. Today we'll be talking about the environmental impact of aluminium can production. This video will be broken up into 3 sections: primary aluminium production from raw materials, manufacture of the cans themselves, and then finally the effects of recycling. I'll leave timestamps down below so you can jump to the relevant sections, and you'll find a literature review linked below which lists all of the sources that I used in coming up with this research. So this video and the one to follow began in the supermarket. I was in the beer aisle and I was just trying to figure out if I should buy beer in aluminium cans or glass bottles. I wanted to pick the most environmentally friendly option, but I had no idea which was the least harmful. I figured either was better than plastic bottles, but I had nothing really to back that up. So I went home and I Googled it. And then I fell down a little bit of a rabbit hole because there's actually not that much information out there. The first articles I found that suggested that it was a bit of a wash. Aluminium is quite resource intensive to produce, but glass bottles are very heavy, so they take more energy to transport. That wasn't very satisfying, so I looked in a little deeper and I found a few what they call life cycle assessments, where they look at the whole life cycle of a material and they would compare aluminium cans to glass bottles to plastic bottles. And most of these suggested that it sort of went in this sort of aluminium, then plastic, then glass. That also didn't sit very well with me because I can't imagine plastic as like the second most preferred option. And actually when you look a little bit deeper, they're normally just comparing greenhouse gas emissions in the production of this single-use item. But there's a lot of byproducts that come along with the different materials in their production, as well as, with plastic, we have breakdown into microplastics, which is not so easy to deal with. So it's not an apples to apples comparison. So I wanted to do a more in-depth analysis. So today we'll be talking about the full life cycle environmental impact of aluminium cans. Next time we'll be looking at glass bottles, and then hopefully I will do a third video on plastic bottles if there's enough interest in that topic. This is a very new YouTube channel, so if you want to see more, definitely give this video a like and subscribe so that I know that you want to see more of this. And then eventually I will do like a big roundup of all 3 and we'll try and get an idea of which option you should choose in which scenario. Right, so enough waffling. Let's get into the video. So aluminium is an exceptionally abundant material. It makes up 8% of the Earth's crust. However, it's not found alone. It's always in compounds with other materials, so it needs to be processed to extract the aluminium metal. The main ore of aluminium is bauxite, a sedimentary rock that's found mostly in tropical and subtropical regions, consisting mainly of aluminium hydroxide compounds, along with silica, iron, and titanium. The main countries that mine bauxite are China, Australia, and Guinea. Each produced about 25% of the world's bauxite production in 2023. The extraction of aluminium metal takes place in 3 main stages: the mining of bauxite ore, the refining of that bauxite into alumina or aluminium oxide, and the smelting of that alumina into aluminium. Bauxite is extracted using simple surface methods or open pit mining. First, the topsoil and vegetation are removed by scraping them away, and in environmentally responsible mines, that material will be set aside for future rehabilitation of the area. Then the bauxite is removed using a combination of excavators, drilling rigs, and explosives. The only real processing they tend to do on site is crushing the larger rocks into smaller pieces, washing and drying. Then they transport the bauxite via truck, conveyor belt, or railway car to local refineries, or they put them on ships and send them overseas, mainly to China, who is the biggest importer of alumina by far in 2023. Once at alumina refineries, the bauxite is processed using the Bayer method, which was introduced by Carl Joseph Bayer in 1888. In this process, bauxite is mixed with caustic soda under high temperatures and pressures to produce a solution of sodium aluminate and insoluble bauxite residue. The sodium aluminate is then mixed with a catalyst of alumina particles, which causes solid alumina hydrate to precipitate out of the solution. A precipitation is when solid particles form out of a solution. Any remaining liquid is removed for reuse, and then the solid alumina hydrate is washed, dried, and heated at 1000 degrees Celsius to evaporate the water of crystallization, and that leaves behind the pure alumina, which is a fine white powder. And in total, it takes 2.9 tons of bauxite to produce 1 ton of alumina. Bauxite residue, also known as red mud, is one of the biggest environmental issues of aluminium production. It's comprised of undissolved alumina, iron oxide, titanium dioxide, silicon oxide, as well as residual sodium species from the caustic soda. It has a high heavy metal content, and if it's not treated before use, then the bauxite residue remains highly alkaline and can be extremely damaging to surrounding soil and wildlife. Approximately 1 to 1.5 tons of bauxite residue is produced for every ton of alumina, culminating in 150 million tons per year. Only 4 million tons of which is actually used for any purposes. The rest just gets stockpiled in landfills. These bauxite landfills take the form of residue lakes, where you have thick mud settling down to the bottom and then a caustic liquor layer on top. And this alkaline solution can contaminate surface and groundwater, as well as obviously risking human and animal exposure. In 2010, a residue lake in Ica, Hungary burst, releasing 1 million cubic meters of red mud, flooding nearby villages, killing 10 people, injuring 120, and leaving many people and animals with chemical burns on their skin. The sludge eventually made its way into local rivers, leading to mass wildlife casualties, killing all the fish in one river and contaminating the soil. It's now estimated that 5 billion tons of bauxite residue sit in residue lakes globally, with no clear way of using it or treating it to make it less harmful. Alumina is reduced into aluminium via the Hall-Héroult smelting process. In this process, alumina is fed into carbon-lined cells and dissolved in molten cryolite to reduce its melting point to 1000 degrees. A strong electric current is then passed through the cell to separate the constituent aluminium and oxygen atoms that make up alumina. The oxygen atoms combine with the carbon to produce carbon dioxide, while the aluminium sinks to the bottom of the cell and can be siphoned off. It is then mixed with any alloying materials to change the properties of the aluminium and then cast into ingots. For can bodies, 1% magnesium and 1% manganese are added to increase strength and pliability. Over 400 kilos of carbon is consumed during this process, resulting in the direct formation of more carbon dioxide than aluminium, about 1.5 tons of carbon dioxide per ton of aluminium. This process is extremely energy intensive. Producing 1 ton of aluminium requires 2 tons of alumina and consumes 54 gigajoules of energy. In fact, aluminium smelters consume 4% of the global electricity supply, and so they're normally located near low-cost power stations. There's usually hydro, coal, or natural gas. Only 28% of these energy sources are renewable. In total, to produce 1 ton of virgin aluminium requires 5.8 tons of bauxite, produces between 2 and 3 tons of toxic red mud, and consumes 210 gigajoules of energy. The total amount of greenhouse gases emitted depends on the fuel sources used, from about 5 tons with hydropower to 22 tons with fossil fuels, though most reported values lie between 12 and 17 tons. The aluminium industry as a whole is responsible for 3% of the world's greenhouse gas emissions, with up to 2/3 coming from the smelting process. With global aluminium demand projected to increase 40% by 2030, it's crucial that the aluminium industry adopts more sustainable practices. This includes moving to renewable energy sources, removing the need for carbon in the smelting process. There are some techniques in development on this. Finding ways to better manage and process red mud, and to shift focus to recycling and reuse to reduce our need for primary production. The manufacturing of aluminium cans begins at a rolling mill, where slabs weighing up to 30 tons each are heated to 525 degrees Celsius to make it more pliable, and then pressed between hot rollers until they reach 3 millimeters in thickness. These are then further cold rolled to desired thickness and then coiled for transport. For aluminium cans, the final coil sheet is 0.27 millimeters thick and 10 kilometers long. Packaging manufacturers then cut 140 millimeter blank circles out of the sheet and then put them through a series of pressing operations to construct a cup 66 millimeters in diameter. To produce an even edge, the top 6mm of these cups is sliced off and scrapped. A significant amount of scrap is generated through these procedures, which are sent to remelting facilities to produce new ingots. After cleaning the cups, they're printed with exterior branding, and their interiors are sprayed with a 1 micrometer to 0.5 millimeter thick polymer coating. This is to prevent interaction between the can and its contents, and it is necessary to have some kind of coating, as otherwise acidic beverages can eat away the aluminium and contaminate the drink. Coatings make up between 2 to 3% of the can's mass. Very little research has been done on the can coatings. A 2021 study looked at the coatings on beer cans, sourced from 16 different countries, and found a wide variety of polymer coatings used. The most common were epoxy resins based on bisphenol A or BPA. BPA is an endocrine disruptor and has fueled significant controversy over recent years over its potential implications for human health. I'm not going to go into detail about whether you should be concerned over the use of BPA because it's not a subject I know really anything about. But considering there are a lot of people who are trying to avoid products with BPA in them, it's just something to be aware about. This was the only study that I could find that talked about the potential for the coatings to break down into microplastics when improperly discarded in the environment. They fished a solitary can out of the ocean, which did show a significant deterioration of the can's coatings. This indicates that can coatings are vulnerable to break down into microplastics, as well as showing a potential for additive leaching. Clearly, this is an area that needs much more research. The final stage of can body production involves the shaping of the neck to allow interlocking with the lid, before pelletizing and wrapping for transport. The lids and pull tabs are created from a slightly different alloy than the can bodies. They have more magnesium and less manganese for increased strength. After cutting, shaping, scoring, and affixing the tab, the lids are packaged separately and sent with the can bodies to the beverage manufacturers. After washing and filling the can bodies, the lids are attached with the addition of a gas to fill any crevices and ensure an airtight seal. The completed product is then packaged and distributed to retailers worldwide. Primary aluminium production is the biggest contributor to an aluminium can's overall environmental impact. So significant savings can be achieved by utilising secondary, aka recycled, aluminium instead. The general recycling process is as follows. Used cans are collected from the consumer and processed and baled at a waste management treatment facility. These are then sent to remelters who crush them into small pieces, screen them for foreign contaminants, and heat them with a high temperature gas to vaporize the paint and polymer coatings. The emissions released during this vaporization process depend on what type of coatings are on the cans, with plastic increasing the chances of toxic emissions. After melting the cans in a furnace, the cans are cast into new ingots ready for rolling at a rolling mill. Both primary and secondary aluminium production produce a waste product called dross, a solid mass of oxidized aluminium and other impurities that just sort of floats on top of the molten aluminium and must be skimmed off before pouring. Primary aluminium smelters typically produce lower quantities of dross with higher aluminium content, up to 80%, compared to secondary aluminium smelters due to increased oxidation and impurities inherent in recycled aluminium. Salt may be introduced to the melt to increase metal recovery and reduce oxidation. This is then termed salt slag or salt cake, and it has a lower aluminium metal content of 5 to 7% and an aluminium oxide or alumina content of 15 to 30%. How common the use of salt is in secondary aluminium production is uncertain, with sources simply stating that it depends on the quality of the aluminium scrap. Dross can be processed at specialised treatment facilities to recover aluminium and other products. However, unfortunately, most of it, 95%, is currently landfilled, which leads to soil and water contamination due to heavy metal leaching. Interaction between groundwater and rainwater with various elements in the dross produces air-polluting gases, including methane, ammonia, hydrogen sulfide, and phosphine. Because of this, landfill disposal of dross and slag is actually banned in most European countries. Dross and slag production rates vary significantly in the literature. They can range from 15 to 200 kilos of dross or up to 500 kilos of salt slag per tonne of aluminium produced. These disparities likely stem from differences in recycling methods, as well as a lack of distinction between different types of scrap and the interchangeable use of the terms dross and salt slag. The type of furnace also plays a crucial role in dross production. One study found that electric furnaces experience 0.5 to 3% aluminium loss, whereas fossil fueled furnaces produce 5 to 8% metal loss, and this was due to the aluminium metal reacting with the exhaust fumes from the fossil fuels. With such variation in dross and salt slag production rates, it's difficult to ascertain how much aluminium is actually lost during the recycling process. This raises some questions over the long-term feasibility of establishing a fully closed-loop system for aluminium cans without significant improvement to metal recovery rates. Despite this, recycling offers significant environmental benefits. Recycling uses only 5% of the energy of raw production and produces 95% less greenhouse gas emissions. It also avoids the production of red mud and other pollutants associated with primary production. According to the International Aluminium Institute, the global recycling rate for aluminium cans is 70%, with the rest disposed of in landfills, incinerated, or left to pollute waterways and other natural environments. Published recycling rates include both pre-consumer scrap, which is scrap arising from the manufacturing process, and post-consumer scrap, that arising from the disposal of products after they've been used. It is post-consumer scrap that is important in determining the sustainability of aluminium cans. The inclusion of pre-consumer scrap artificially inflates recycling rates and makes determining the genuine post-consumer recycling rate challenging. One study on can recycling in the US found that when including the pre-consumer scrap, the recycling rate was 82%, the actual post-consumer recycling rate was only around 50%. In 2021, a life cycle assessment was commissioned by the Aluminium Association of America to determine the overall environmental impact of aluminium cans and the effects of recycling. They assumed a recycled content rate of 73%, which is the average recycled content rate in the US when including pre-consumer scrap. But as discussed, this is far from the true recycling rate and heavily skews the results. The study concluded that despite only making up 27% of a can's content, primary aluminium production was responsible for 40% of the can's global warming potential. Manufacturing was the second highest contributor at 24%. The study used a functional unit of 1,000 cans with an average size of 402 mils each and a combined weight of 13 kilos. The total primary energy demand and global warming potential over their lifetime, including end-of-life disposal and recycling, was determined to be 1.63 gigajoules and 98.6 kgs of carbon dioxide equivalents, respectively. Additionally, the study claimed a 43% reduction in the carbon footprint of aluminium cans since 1991. This was through efficiency improvements in primary production and can manufacturing technology, as well as a reduction in average can weight. However, they also found that recycling rates in America had declined significantly during this time, decreasing from 62% down to 50%. The cause of this decline was not discussed, but may be due to the removal of deposit return schemes, as well as the increase in mixed stream recycling. To illustrate the significance of recycling on reducing aluminium cans' environmental footprint, the study compared 1,000 cans made from 100% primary aluminium versus 1,000 cans made from 100% secondary aluminium. Assuming the primary aluminium was sourced from China, which has a heavy reliance on coal to fuel their smelting activities and therefore represents the upper limits to aluminium cans' environmental footprint, the study concluded that production of 1,000 cans using primary ingots required 3.7 gigajoules of energy and produced 358 kgs of carbon dioxide equivalents, whereas using 100% recycled aluminium reduced the energy requirements down to 758 megajoules and emitted only 42 kgs of carbon dioxide equivalents. This represents a 79% decrease in the energy requirements and an 88% decrease in emissions. However, the accuracy of life cycle assessments like this heavily depend on the quality of the input data. In this case, the study used data that claimed 13 kgs of primary aluminium required 611 megajoules to produce and emitted 38.4 kgs of carbon dioxide equivalents. As we saw in the first part of this video, the production of 1 tonne of primary aluminium requires 210 gigajoules of energy to produce and emits between 5 and 22 tonnes of carbon dioxide equivalents. Extrapolating from these figures, the production of 13 kgs of aluminium should require 2.73 gigajoules of energy and emits between 63.8 and 283.4 kgs of carbon dioxide equivalents. This is significantly more than is stated in the study. This substantial disparity, along with the conflated and misrepresented recycling rates, show how important it is to critically evaluate the information we receive, particularly the sources of that information and any biases that may be present. Most of these reports are produced not by independent scientists, investigative journalists, or NGOs, but by the industries most likely to benefit from positive reporting, in this case, the aluminium industry itself. Despite the issues around the reliability of published figures, recycling clearly offers significant environmental benefits. The more cans we recycle, the less need there is for raw materials, meaning less energy consumed, lower emissions, and less red mud piling up. Cans made from primary aluminium generate up to 46 times their weight in greenhouse gas emissions. Switching to recycled aluminium reduces this down to just 3 times their weight. And while this ratio is still relatively high, aluminium's high strength to weight ratio means that cans can be made from very little material, resulting in lower emissions per beverage compared to single-use glass or plastic bottles. Most life cycle assessments, including those from independent scientists and organisations like Zero Waste Europe, conclude that aluminium cans are the most environmentally friendly single-use beverage packaging option, at least for carbonated beverages. However, these assessments rely primarily on emissions comparisons, which, as stated, heavily depend on the quality of their input data. Factors unique to each packaging type, like polluting byproducts or environmental degradation, are much harder to quantify and compare. With annual can production expected to increase from 420 billion in 2020 to 630 billion by 2030, there is a pressing need to improve recycling rates. Despite published recycling rates of 70%, the actual post-consumer recycling rate is likely much lower, probably closer to 50%, and declining in some regions. But achieving a circular system isn't only reliant on the responsible recycling habits of consumers. Recycling processes must be improved to reduce waste and ensure that no aluminium is lost from the system. Governments need to impose regulations to enforce more sustainable practices amongst packaging manufacturers, as well as to ensure precise monitoring and transparent reporting. Only then can we understand the full scale of the environmental impact and decide whether systems can be improved. So I hope you found this discussion on the environmental impact of aluminium cans interesting and informative. If so, please give this video a like. That'll help me get this information out to more people. And don't forget to check out the literature review linked in the video description below for more details and a list of the sources that I used. Next time we'll be repeating this analysis for glass bottles, so if you don't want to miss out on that, subscribe and I will see you in the next one.